So for any of you guys that don't know me or don't remember, my name's Ben, the treasurer for FSAE. I also work with the powertrain on the IC car, and I'm going to do how to design a part for FSAE today. It's going to be pretty basic information. Some of you guys might already know this. It might be things that when I say it, it just seems obvious, but this is supposed to be a flow chart and a guide for when you design anything. Any part outside of here, everybody's going to follow these same guidelines. I'm going to tailor it more towards FSAE, in which parts you'll kind of have more of an emphasis on. But when you go anywhere, the general outline for this is going to be pretty much the same. And so this is pretty much what we're going to go through in just a nice, easy chart. Defining the problem and doing your background research. You can kind of see that that's two arrows. It goes back and forth. That's almost one step. So whenever you start any problem, you'll wind up needing some sort of goal and some sort of guideline to do that. And you'll bounce back and forth in setting that guideline with the research or figuring out what you're doing. Specific requirements. That'll be after you do your guidelines. What are your hard numbers that you're aiming for? Temperatures, torque, all those set numbers that you really need to have. You'll either dictate them as parameters when you're operating or possibly through the rules, and we'll get more into it. That section, define the problem, do the background research, and specify your requirements, is probably the most crucial and the most boring. And there's just not a great way to get around it. You're going to need to do your research. You're going to need to figure out your goals. It's going to be a lot of reading. You know, sometimes even full chapters in texts and figuring out what you need to do. But it is crucial that you have that set up, because if you don't have that set up, it will affect the rest of this flowchart pretty strongly. And then after that, you start getting into kind of the more interesting things where you brainstorm, you evaluate, and you choose your decisions. I don't go too heavily into the brainstorming because it varies a lot with each part, and I go over some basic stuff on the evaluations and choosing your solutions. I even touch in a little bit on trade studies. Develop a prototype and solution, and then testing that solution. That's where FSAE kind of differs a lot from the standard engineering model. And I'll go more into that once we get there, but we are pretty simulation heavy compared to actual prototype heavy. And then communicate results, and does the solution meet the requirements? That's just the results of either your analysis or talking with your team and going through all that. So the acknowledgements, I kind of already made this clear. We don't always get to follow this path. We're designing a full race car within about a year, maybe a year and a half if you start over summer and you actually work hard. That is not a lot of time. If you're, especially as a new team, or if you're starting a new vehicle, a year to develop, prototype, test, and then compete is an extremely tight schedule, especially since we're in school, right? Like this is not that would be a hard schedule for a full-time job, let alone the competition and the school that we're doing at the same time. And you'll inevitably run into, I wouldn't say conflicts, I'd say differences of opinion on which parts you need to focus more heavily on. A lot of people will skip one section and go really heavily on another, and so you got to work with your team to kind of figure out the right balance for each part, and each part is going to differ. So, starting with defining your problem, and it'll be a little, this will seem kind of hard because I'm not doing the slides on your background research until after this, and you'll see how they both kind of tie in together. Let's say next year I come up to one of you guys, I come up to Pavon and I say, design suspension. That's a huge goal, right? And it seems overwhelming. There's a lot of things on suspension that you're going to need to design. But that's not unrealistic with FSAE. Like you're going to have to take responsibility, and you're going to have to do a lot of different things. And what this really does is defining the problem is you're breaking it down and you're just taking it step by step. Don't look at every single thing you need to solve. Start with your first thing. What is the goal of the system, right? What are you supposed to do overall? And so for suspension, you're looking at connect the vehicle to its wheels. right, at its most basic level, and then try and give the best rolled holding, handling, and braking as possible. That's your system level goal. There's no numbers in that, there's no calculations. You haven't even defined any, or you haven't even designed anything. You know, just figure out what you're supposed to do as a whole. And again, you're going to have to do a lot of background research to go back and forth between that to define that goal. And we'll kind of go into some of the sources a little bit later. Once you've decided what you need to do on that system level, then you can start looking into each individual parts. So you'll start looking into the bell cranks, shocks, A-arms, mounting brackets, steering, etc., and defining each one of those as a goal. You don't always have to write it down. It's not like you're going to make a document necessarily of every single part and each one of their goals, but mentally you need to do that checklist. You need to say, here's the steering, what does the steering need to accomplish? What am I designing around? And it seems simple, right? Like I'm saying this and all you guys are saying that, yeah, no kidding. Like the steering has a goal, you should keep that in mind. But you'd be surprised how many people jump into a design without a clear goal in mind. They'll just either be copying or they'll be trying to iterate a design without knowing what they're actually doing or what their goal actually is. So it is important that you start with that foundation. And then the second step, why is it important to solve? Again, with the limited time, you're not going to be able to solve every single little issue. So you need to pick out, in my mind, there's two different type of problems you can solve. You're either going to solve functional problems or you're going to solve performance problems. And your functional problems are going to be what makes the car work, right? What do I need to get done so that its wheels roll and we're going to be able to compete in competition and just pass, like just get across the finish line. And those goals will stand out pretty clearly. And then the second part on top of that is, performance-wise. Do you need to solve making this piece go under 10 pounds? For performance-wise, yeah, that'd be great. You lighten the weight of the car, and you're going to have a better race car overall the lighter you get. But that's not going to be something that is make or break it if the car runs. And so, you'll wind up figuring that out relatively easily, and just keep that in mind. One of the terms, and I'm very guilty of this. I want to make a part really good, and I want to analyze it to death. But I think it was actually Kyle that told me, don't get stuck in analysis paralysis. And you can make a part better infinitely, right? You can never perfectly optimize a part. Like it can always be improved. So just keep it in mind with your timeline on what you need to do to make it functional and what you need to do to increase its performance. For the background research, I'm kind of just going to go over different areas that you can go to. A lot of people, the first thing you'll do is go to Google, which is good, that's fine. That's a good place to start. And what it'll probably lead you to is the second one here, where you go to different websites and you go to FSA forums and other team websites. But it doesn't always answer the questions you're looking for, or in the depth that you're looking for. An example that I can think of is the restrictor on the car intake. I didn't really know how to calculate the flow that was going to go through that. And some people define it as a restrictor, and you might be able to use some physics forms to kind of define that. But what really wound up helping me a lot was this SAE database here. And it won't pop up on your Google searches. These papers that are on this database aren't just going to show up as that second option on Google. You have to go to the database, and you can do that. You just go to Orbach Science Library, Research Services, Databases, SAE. And if you do it through Orbach, we have access to it. Not everybody has access to it. Usually you pay a full membership fee of $200 and something to be able to have access to this database. The school buys the license to be able to go onto that database, and we have full access to it. So every paper published by SAE. And a lot of those papers will be like senior design projects from other FSAE teams. A lot of them will also be just regular SAE papers on propulsion landing systems for Mars and a bunch of crazy stuff you'll never really need for FSAE. But those other team papers are really useful because that's guys who have probably been working on something since freshman year till senior year, and then publish this paper gradually. That's 4 years of experience condensed down usually into 10 pages, right? With diagrams, with explanations, all their equations. It's invaluable on how much that is. And again, with the forums and the databases of questions on FSAE.online, if you ever have like a rules question or if something's going to be allowed, going to FSAEonline.com, you can see all the questions that other teams have asked. And they're answered by the judges, which is the clearest, best answer you can have. As a matter of fact, if you see like a question and then an answer that you were really nervous about, you'll probably screenshot that and have that ready for competition just in case the judge comes and is saying something else than what you read. That is pretty much evidence on, this was approved at some point. Now it might differ from year to year, but keep that in mind.
But one thing I want to add to that, the rules actually say if you do get something clarified, you should print every single rules question you asked out and put it in a binder. And you bring that with you to competition.
Yeah, so you can ask questions as well, right? Like as long as you'll basically get your SAE International and you'll put on there, I'm a part of this team or registered team just in the drop-down box. That'll go to either Sammy or Kyle and they'll approve you as being on the team and then you can ask questions directly to the judges. Run that by your sub-team leads first, obviously, just to make sure you're not asking questions on behalf of the team and we can kind of give you our format and everything, but it's an invaluable option. This last part here that I'm always hesitant to say, you can directly contact other teams. If you see a picture on Facebook from one of their teams or LinkedIn or something like that, and it looks like they solved an issue that you are directly dealing with, it's not terrible to reach out to them. Whether they give you a direct answer or are willing to help you out is a totally different story, but a lot of guys are really helpful. We're all just trying to get to competition for the most part. You might wind up, if you try asking Texas A&M how they did their control systems, and if you could send them a screenshot of their controls, it's probably not going to happen. But basic questions on maybe what resources they used or who they talked to or what their sponsors are is usually okay. And again, run that by your sub-team leads and the team leads before you do that. Alumni are a great resource, just don't overload them, right? You can look at past year's designs. A big example of what we've been doing a lot is contacting Joey. Joey designed our electric motors, and he graduated and we'll be using them this year. So we do reach out to Joey a decent amount, but don't expect them to dive in and tell you every single little detail of how you need to design this. If they do, that's awesome, but more likely than not, it's going to be something within 2 sentences. Like, I use this website and this equation. So make your questions brief and try and be as concise as possible. Then the same thing with professionals and professors. The professors here, depending on how excited they are when you pitch it, will vary on how much time they want to put into it, right? They don't have any direct reason to help us. They're a great resource, and a lot of times they are willing to help us, but going to him and asking, how do I run this full ANSYS simulation, he's not going to sit down with you for 2 hours and set that up. Make sure you have your questions prepared ahead of time and that you're concise and know what you're probably going to get out of it. All right, so that was, for the most part, specified requirements. So a lot of the requirements or the specifications that your part will go through are going to come from the rules, right? So let's say you've gone through your background research and you've defined everything on your goal. Now it's time to get those hard numbers. The first thing to do is read the rules for that part. So like we were talking about before with suspension, read through all the suspension rules, right? Those restrictions will a lot of times define some of those parts. The belt cranks and the forces that can go through it, what suspensions are allowed and not allowed. You don't wind up having to spend the time on a system that would not even be allowed, right? And having those size constraints and everything are the basic kind of specifications that you would want. And then the other specifications are just like operating parameters. Like the motor's going to overheat if it goes above 60 degrees C. Like, that's a pretty basic thing to say. the highest temperature that the motor can get to is 60 degrees C. Even if the rules don't say that, you know as an operating parameter that's not okay. You know, and as we go through dimensional requirements, some of the rules will have deflection requirements. If you have a really complicated linkage or something like that, you'll probably specify your own deflection requirements and your stress requirements, thermal requirements, electrical requirements. You need hard numbers though. That's the key thing with this step, is go from that concept to the actual like temperature max equals this, velocity max equals this, you know, all that, and try and actually write those out. This will be an area you're looking into. Now I did the intake manifold on the internal combustion car, so this is kind of some of the stuff that you'll see in the rules. I screenshotted this directly from the rules. You know, this part right here is literally giving me the layout that I can have. Throttle body, restrictor, engine. A lot of cars run the throttle body right on top of the engine, so that gets rid of a lot of research on my end on what I could have possibly been doing. This turbo pump simulation I'm not even going to go into. The actual size constraints on where it can reach out to, you know, this is going to define a lot of, so on our car, you take like a horizontal plane from the back of the tire all the way up to the top of the roll bar. Nothing can exit that, right? So that right off the bat is going to limit your size constraints on what you're going to be able to do and what you're not going to be able to do. And if you ever have a question on a rule, again, you'll format it in a way where you kind of like take this rule number here and ask a question. They'll have a drop-down box for that. Other specification requirements, know your manufacturing limits. Kyle is actually talking about doing a manufacturing lecture relatively soon, and you guys have gone down to the machine shop and seen what we're capable of doing. When you design a part for a mill or a CNC, you need to know what radiuses that your inside pockets are going to be able to do. You know, no hollow chambers without being able to get to those hollow chambers. And that seems really obvious, but that's happened, right? We've had people design stuff where it's just hollow in the middle, and you're like, how are we going to mill that out? You know, are you cutting it in half and welding it together? What are you thinking here? Because you can't just magically make something hollow. And again, it seems obvious, but manufacturing, yeah. This is definitely something not going to be taught in classes. You will never have a class teaching you the manufacturing limits of a shop, here at UCR at least. This is something you're going to learn either through us or possibly through the research labs. But this is a huge skill or knowledge to have when you go into the market, because our manufacturing limits are usually the general manufacturing limits of most companies. All right, so getting on to the more fun stuff, the brainstorming and solution selection. So there's a lot of variability here with each part. Some things you're not gonna, like I say here, come up with at least 3 different solutions. Try and force yourself to think of things outside of the box, get a couple different solutions on hand, but sometimes due to the rules or just due to the general operating parameters, there's really only one design that's going to fit. Not always, but sometimes. You know, it goes back and forth. Again, like I said in the beginning, take it with a grain of salt. If it's restricted so that you can't do anything else, then obviously you're not going to be able to come up with 3 different solutions. But if you are able to come up with 3 different solutions, or maybe you just have infinite amount of solutions, maybe the rules are incredibly vague on what you can do, which is true in some of the parts. You can do a very basic trade study. That PUG method there is a real basic one that can help you select it. This is not something that we usually do too often on FSAE, because setting it up can sometimes take some time, and it's usually pretty obvious what's going to work best. But if you're all over the place, you don't know what to select, I've got try and use geometric constraints. Try and make things parallel. Try and use as little hard constraints as possible. Hard constraints being this segment is 3 inches. When you go back and do your redesigns, which you will do, you will thank yourself for having those geometric relations and just being able to change 1 or 2 hard constraints. And again, it seems kind of obvious now that, you know, if you have 10 geometric constraints and one hard constraint, and you just change that hard constraint, everything else just proportions out correctly. It's obvious, but it does take a little bit getting used to try and design a part around parallels and 90-degree angles, coincidence, different kind of geometric constraints. Prototyping. We don't always get to prototype. As a matter of fact, there's usually very few parts that you'll actually get to prototype. It just comes down to time. It comes down to time, and it comes down to money as well. You know, making a prototype is kind of expensive. When you go to a company, you'll a lot of times make a prototype, and you'll put a ton of sensors on it, and you'll spend months testing that prototype, getting ready for your final design. A lot of times, the first time you manufacture something is when it's going to go onto the car. And I'll get a little bit more into how we actually kind of validate different designs with simulations in a little bit when I get to testing. But you know, if you can do some sort of 3D print or something to verify the geometry or just make sure it's okay, you can go for that. Some things need a prototype. The batteries, for instance, like really needed a prototype. The uprights may or may not have a prototype on the gearing, things like that. Your complex systems are going to have to. And the one thing I can say is if you absolutely need a prototype to validate your designs, do not push it off. It takes a long time to make that prototype and set up that testing. If it's an absolute necessity to validate that design, start moving quicker. And however fast you think you're going, go faster, because it takes a long time. And that's the biggest constraint with FSAE. And then improving on designs from year to year. So this kind of fits in with that prototyping, especially what you guys are sophomores for the most part, juniors. Juniors. You'll get to design for this year and possibly even next year, depending on if you're going to start working on next year's car or anything like that. Anybody that's a sophomore is going to get even more time to start actually iterating on those designs. So don't feel too bad that you don't get a prototype, and you'll be able to improve on your designs from year to year, or at least teach people how to improve on their designs from year to year. This is kind of an example again. The one on your left is the first intake I did sophomore year, and the one on the right is the one that I did last year. And it obviously improved a pretty decent amount. Mostly because this beautiful CAD design right here had a carbon fiber plenum, and it imploded and then caught fire. So, which is fine. Yeah, it's fine. This was made maybe a couple days before competition, and it all comes down to that learning curve and figuring things out. And luckily we had this ahead of schedule, and we're able to make something else that at least worked. And then everything after that, you know, using 3D printing and advanced geometries, improving on my calculations. I built that thing like a tank. That thing's, any backfire the engine's going to give, which it's been through a lot already, has been able to withstand. So I'm calling that improving designs, and I'll show you some of the testing that I was able to actually do with it to show that it did improve. All right, so simulations. This is how you're going to validate most of your design to your judges, right? When you go up and you say, this design works because of this, this, and this, they'll ask, what calculations did you do? What simulations did you do? Show them to me to prove that this is going to work. And so the very first thing you're going to wind up doing is doing, I call them napkin calculations. You can call them back of the hand calculations, but whatever you want to call them, something quick. Don't spend a ton of time trying to do a perfect hand calculation. There's just too many variables in the real world to do a completely accurate hand calculation unless you're set up in a perfect scenario, which is never. Do something where you can make some assumptions and do a quick validation to tell you whether you're heading in the right direction or in the wrong direction. After you do that napkin calculation is when you can start getting into some of the more advanced simulations, not even advanced, just simulations in general. That's when you start doing your stress analysis on your belt cranks, or you start doing the fluid simulation through the batteries. Start adding fins into different areas and seeing where you can improve. Now, when you do these sims, and this kind of goes all the way back to specifying those requirements, You need your boundary conditions, which is kind of just like those operating parameters, right? Like, what's the maximum temperature that this can get up to before it fails? What kind of flow rate do I need to see going through this to be able to validate it that it's going to work? All those requirements that you made in the beginning are now going to play a huge part on validating your part on whether you've designed it correctly. And a lot of people get lost on figuring out these boundary conditions and having to go back to specifying the requirements, learning something as they're specifying those requirements, redesign their part, and then come back to this. So do it in the beginning. It'll save you a lot of time and it'll save you a lot of headache. Most of our simulations are done in SolidWorks. We have a full license key just about every year with SolidWorks, aside from the school key, so you can do those thermal simulations and those fluid simulations. And we'll probably have like a tutoring day on setting those up and actually running those in SolidWorks. If you're feeling real gutsy, you can start learning ANSYS. ANSYS is solely a simulation software. It does some very basic modeling, but it is solely a simulation software, and it can get complex, but it can also be more accurate, and it can help set things up.
One thing I wanted to mention is we do have a sponsorship from ANSYS, and using that, you guys can access their webinars. So if you want to do like pace yourself and learn at home, you can definitely do that. And then we also have access for SolidWorks training that's online also via Linda. So there's always ways that you guys can work on this yourself without waiting for us. Like if you want to take the initiative and start learning it yourself, there's definitely that there for you guys.
Yeah, I should have added Linda actually to the background research type of area, mostly for trainings, but the school gives us access. It's like lynda.com.
Yeah, Linda with a Y.
Linda with a Y. But they have amazing tutorials, probably better than you're going to find anywhere else for ANSYS and for SolidWorks and just about anything else that we're going to really do software on. Okay, so physical testing. Again, just like I mentioned, how doing a prototype is kind of rare or not always accurate. You know, you're not going to make a prototype of every single bracket, test that bracket, and then make the final product. A physical test is also probably not going to happen for a lot of pieces. It'll happen for the larger systems and for some other pieces, but don't spend a ton of time validating a smaller part on the car when there are bigger issues and other parts to design. So again, if you are going to do a physical test, start moving very quickly and getting some things done, because they do take a long time to set up and make sure that they're correct. Again, knowing those boundary conditions comes into play here quite a bit. And then if you do a simulation or a physical test bed, see if there is a company that designs a product that is similar to what you're making, and see if you can reach out to them and use their test bed. I mean, I don't know, so Ian, when we're looking at the batteries, I think CSERT is donating some time on their...
Yeah, so we have a actual battery testing machine that not just tests batteries, but can actually take current and time inputs. So it can actually simulate a real driving pattern that you can see on a vehicle. And so we have that at CSERT, and then we have Jeffrey, who's a PhD student over in Winston Chung, where they do battery research and they build their own batteries, and they have a similar machine, but their goal is to test each individual cell versus like...
Yeah, so I mean, you know, setting that up ourselves is a huge time commitment and not something that's capable within the scope of a year. You know, just getting the battery pack done in itself with a prototype is a hard schedule. So reach out to other companies. You know, me and Danny went to AFE Power and used their flow bench for our intake. You'll see some teams try and design their own flow benches, things like that. Save yourself the headache, see if you can reach out to a sponsor and use their test bench. It saves a lot of time, and it will probably be much better than what we could make in our time span. So this is, you know, and again, I never got to do a prototype of the intake. This is me improving on earlier years designs. I never did a prototype intake and then an actual intake. But since I was there for sophomore year, I was able to build on my designs and actually compare them to see if we're doing better. Having that specification of what you're trying to improve upon or what your limiting factors are is really important when you start looking at what you were trying to improve. So here, for the most part, it's all about flow rate coming through it and your pressure drop. So testing both the intakes and getting the pressure drop difference between them and seeing if you're improving was kind of a specification that I had early sophomore year, was make sure the pressure drop is as low as possible, and then junior year it was make the pressure drop less than it was sophomore year. Right? Always set that goal when you start designing. And it did come out well, and if you can do a physical test or a simulation, because I do have pretty much this exact same thing that I did through ANSYS, because ANSYS will tell you this info. Is it as accurate as a real simulation? Nothing's as accurate as a real simulation, especially on flow, which is kind of why I opted to reach out to AFE Power and see if we could test it to see if I could verify my goal. But the simulations a lot of time will be more than enough proof that you're improving upon yourself and to show that the judges that it's worthwhile. Yeah, go ahead.
What if you have no basis by which to compare? Let's say you're making a design that you, like...
Starting from scratch, yeah. Yeah, and I was there with the sophomore year. It's do as best as possible. For me, it was make the pressure drop as low as possible. No basis for comparison, and that is hard, right? That's an ambiguous goal. And usually you want to define those goals as best you can, which is why I was very happy to just be able to say, make it a better pressure drop than 2016. But yeah, that is a challenge. If you can get data from another team, or you can talk with a professional, reaching out to alumni, seeing what they were kind of in the ballpark for to see what you should be aiming for, then that's also very good. That's a good way to set your goal for what you're trying to design and what you're trying to have it operate around. And I think this, for the most part, oh yeah, why do this? So this is going to lead you to the best part. Doing this process and working through it, and it seems simple, it seems obvious, but it is nice to have that flow chart of each step of what to do, and at least breaking down each component and trying to figure out or knowing what steps need to be done to actually make that component the best as possible. It's going to be different a little bit for every single component, but in general, this is the guidelines that just about everybody follows. So not only are the judges looking for this, recruiters and anybody that's going to be looking to hire is also looking to see engineers that take this process. This is not something we get to practice a lot in school. So people that have experience going through this process and knowing about it, and when you go into an interview and they say, how did you make this? Taking those logical steps and explaining out each part of it is what they're looking for. And again, every good engineering company does this, and the judges need it as well. I mean, it's a big part of our design points to be able to show the judges a logical process with numbers, data, or whatever you can have, simulations, to show that this was the best we could do for this scenario. And I guess my last little bit to kind of prove this is I was debating on whether I would copy this into here or not, and I decided to. I have been talking with Blue Origin, which is a rocket company, and this was the advice they gave for when applying for the new grad position. A new grad position is usually like a rotational program you do within the company. And the biggest thing that stuck out to me to know that I was doing things correctly and doing what they were looking for was right here. It is best to have a great diversity in number and kinds of things you have designed, built, tested, wrote, redesigned, rebuilt, etc. Right? That's the exact process that we're talking about here. And using that logic, going through, doing simulations, improving upon it. If you can do a physical test, do it, working through those areas. And in my mind, the broke, redesigned, rebuilt, I did a simulation on it, and it failed that simulation. It failed those boundary conditions. In my mind, that is also a logical step to be taken. It doesn't have to be a physical piece. And then it was also kind of cool to see like experience you're involved with, this hands-on engineering, e.g. like literally the first one was us, which was a very nice indicator that a lot of top-tier companies are looking for us and just kind of validating for them. And then other than that, that's pretty much everything that you'll need to know to just go through the basics of designing a part. And obviously you're going to go a lot more in depth, but hopefully just being able to look at this, see if I can get to this roadmap, will at least show you where to start. You know, we're not just going to throw you in. It's not like you need to be having a design done and then the simulation's done within like the next week. Like take these steps, define your issues, define your problems, do your background research. And that ought to do it. That pretty much covers it. Is there any questions from anybody? I think specific, you guys don't have any interest in like, you know, where you're going to start with suspension or batteries or anything like that. Okay. I mean, what did you define as your beginning issue?
So for battery, it's a very unique thing because we've never done EV car before. So the way we started off with was we determined, okay, we're going to use all-wheel drive for motors. Then we took a look at the racetrack and we kind of it was unique because we worked backwards rather than forwards. And sometimes you have to do that. It wasn't a very normal thing to do, but because the batteries power the motors, and then you have to figure out how much energy draw we would need, you essentially have to come up with your list of parameters, and those are hard set. Those are things you cannot change. So once we figured out, we need to use this much energy, we need to race for this amount of time, we took a look, on Google Maps from a top-down view of the layout of the track, and then plugged that into MATLAB and figured out how long the track was and where our problems area were going to be. We determined the types of batteries we could use. We could use 18650s, which are cylindrical, which are similar to what the older model Teslas use, and a lot of teams actually do use 18650s. But we started looking at are there other options? And so you essentially put all your options out on the table, and then you sort of list them in order of importance, and then determine which one works best for you. And from there, you can pretty much narrow down your design to, use this type of battery, and use, this amount of, energy you can deliver. And then the hardest part was really the cooling. Pretty much all the teams that make it to the EV competitions overheat their batteries. Like 70% of the teams do that. And, it really sucks because, you not just lose the practical points when you compete on the track, but you also lose design points, because that is a major design factor. So if your batteries can't run for the amount of time it's on the track and it overheats, the judges are just going to go ham on you.
Yeah.
And they're going to say, why didn't you run the thermal sim, or why didn't you do the research? And they're, really going to look at that.
So, the basic, and if Ian was telling this to somebody who didn't really know what it was, it just sounds like a ton of steps that are just kind of discollaborated. But I literally heard define the problem. He worked back from the motors to help define that problem, but he still defined the problem. Did a ton of background research, found different types of cells, what are other teams using, specified his requirements off of that, then listed all of his options down and chose the best option, and then develop and prototype is kind of where you're at right now, doing all your sims and everything. So, it's not magic that this info just gets pulled out of the air. Ian didn't have all this info before he started doing this. He just followed this roadmap, and you're able to design a part. And I mean, John, you're doing the controls right now. What's kind of some of the steps that you've taken to actually design that?
So basically, we were looking at a lot of the physics of what the car might have to go through and what we'd have to do to counteract a lot of the shifts in the car. So the first thing we had to do was figure out the hell is a control system, especially for this kind of design, like what the logic would be to what you would have to fix, because control system is something that fixes itself. So what do you have to fix? Right, so that was like the first question we had to answer. I'm specifically doing torque vectoring. So it was adjusting the torque on each individual one of those motors that he was just talking about. So from there, it was how are we going to distribute that torque? Why are we doing it this way? And once you go through that logic of process of figuring out what you want to do with it, then you kind of have to realize the next step is making something to make that occur, right? So we used MATLAB to make that kind of logic happen, converting it to C+, to C, and right now we're testing it. So, the process will only keep going. If something goes wrong, we're gonna have to do a redesign, redo it again. But, that's just the basic idea. And of course, the same thing happened with the plenum you showed earlier.
Yeah, John also worked with me on the plenum last year. So it's the same type of
process.
Yeah. This process doesn't change. This is the basic engineering process. So I kind of thought it was important to show you guys and just make sure that we're all on the same page, and hopefully it helps you guys out. But I think that'll end the presentation. We'll get out a little bit early, and next week, if the schedule stays how it is, it should be uprights and motors and gearing. So hopefully you guys will be able to make it with that.